We present FuseCap, leveraging large language models for enriched fused image captions. Generally speaking, image captions are textual descriptions of an image that provide context and understanding of what the image depicts. Current solutions for image caption generation use multimodal neural networks to find intermodal correspondences. They process images and generate corresponding texts which describe the images. This field has seen substantial progress with the advent of vision language pre-training, VLP. The process involves large-scale pre-training using web image text pairs and subsequent fine-tuning with human annotated captions. We note that current caption generation models suffer from a significant drawback. Even though images are rich sources of information, the generated captions often lack detail and overlook key semantic elements. For example, for this image, all leading models generate variations of a concise general caption of a person surfing a wave. In this work, we would like the model to produce additional details such as the surfer being barefoot, her long brown hair, the color of the surfboard, and that she extend her arm for balance, all while maintaining a natural and coherent caption. The origin of the caption generation drawback can be traced back to the data on which the models have been trained. This data often omits fine details and frequently misses essential aspects in the images. Therefore, we choose a data-centric solution. We aim to enhance existing datasets. Given their huge scale, manual annotation is unfeasible, leading us to pursue an automated approach. We enhance the existing datasets by employing visual experts to provide additional visual information. Then, we leverage large language model for information fusion. The vision experts we use include an object detector capable of detecting up to 1,600 different classes, an attribute extractor that can extract 400 different attributes for each detected object, and an optical character recognizer that detects and recognizes text within the image. Then, the original caption and the visual expert outputs are fused together using a large language model. This LLM fuser, which is based on ChatGPT, is prompted with the outputs from the visual experts in the original caption, along with a request to generate a comprehensive and concise caption of the scene. This prompt also provides basic spatial context where the expert outputs are arranged from left to right. In this example, the original caption was a woman is holding a tennis racket at a game. The new Fuse caption, maintaining fluency and coherence, enriches the description with an additional details, such as the yellow Nike shirt, the black shorts, the Emirates airline branding on the blue wall, her raised end, and so on. Our goal is to create a large-scale enriched dataset while maintaining a low-cost and open-source solution. We use ChatGPT as an annotator for 20,000 examples, and then we fine-tune an open-source FLAN T5 extra-large model using these fused examples. This trained model is then used to fuse a large-scale dataset, resulting in 12 million enriched captioned image pairs. Here, we can see additional examples of the FuseCap dataset. Take the upper image for instance. The original caption is two men with eyeglasses looking at something, while the FuseCap caption is much more detailed and comprehensive. Two bespectacled men, one with black glasses and a black and brown beard, the other with silver glasses and short brown hair, sit together with an open blue laptop and a table in front of them. A great cat lounges nearby. To evaluate our data for descriptiveness while maintaining accuracy, we conducted a human evaluation on the dataset consisting of 40 participants. Each participant was presented with 20 captions and their corresponding enriched caption, along with the following question: does caption 2 provide an additional meaningful and truthful description of the image compared to caption 1? The participants find the enriched captions at least as good as the original ones in almost 73% of the images. For quantitative metrics, popular choices for caption evaluations are n-gram based. This solution is unsuitable for our case, as it is based on ground truth reference captions. Consequently, using such metrics given the nature of current datasets will fail to capture the full descriptiveness of the captions. Therefore, we compute clip score, a metric that measures the alignment between images and text using a pre-trained clip model. This approach is particularly suitable for our case as it is reference-free and has been demonstrated to correlate highly with human judgment. As can be seen, the clip score of the FuseCap dataset is higher than the score of the original captions across all enhanced datasets. As an additional quantitative metric, we use image text retrieval. This task aims to accurately find relevant images based on textual descriptions or vice versa. Since accurate additional image details can serve as the discriminative factor, retrieval performance can be used as a successful metric for measuring captions descriptiveness. We use a BLIP-based retrieval model and show that when trained and tested on the FuseCap data, the retrieval performance improves significantly compared to the models that used the original captions. Finally, we use the enriched dataset to train a caption generation model. The generator is based on a BLIP architecture. To enable longer and more detailed caption, we increase the maximum content length. Following common practice, we first pre-train on large-scale Fuse dataset and then fine-tune on the Fuse Coco enriched dataset. These are examples of the generator's output compared with the other leading models. As one can observe in the upper image, our generators differ significantly. Unlike all leading models, the output for the surfer image caption now includes all additional details we aimed for: her long brown hair, her white surfboard, and her extended arm for balance. Similar to the earlier approach for quantitative testing of the caption generator, the evaluation is carried out using clip score. We can see that our model surpasses all leading models in performance, despite them being trained on significantly more data and having a considerably higher number of parameters. We also measure the image text retrieval performance when using the generated captions as the retrieval text. These generated captions maintain a high retrieval rate in compared with the original ones. Moreover, they preserve the accuracy of the enriched captions the generator is trained on. This contrasts with the retrieval using captions generated by the model trained on regular captions, which experiences a significant drop in retrieval performance compared to its corresponding model. Typically, a vision language task involves pre-training with a large scale of regular captions, followed by fine-tuning for a downstream task. In this experiment, we investigated whether generating enriched captions could be effectively treated as a downstream task. Our findings show that following this standard paradigm of pre-training on regular captions and then fine-tuning the model to produce enriched captions yields a significantly lower caption generation score compared to the pre-training and the full FuseCap dataset. This outcome validates the necessity and advantages of the large-scale dataset we developed. To conclude, in this work we demonstrated current state-of-the-art captioners produce oversimplified caption. The reason for this can be traced back to the dataset they are trained on, regardless of the model architecture. To address this, we propose FuseCap, a generic approach that enriches large-scale caption dataset by fusing the original captions with the outputs of visual experts using a large language model. We demonstrate that this enriched data can be used to train a captioner that surpasses all others, even though its model is much smaller and trained on significantly less data. Thank you. You are invited to check out an online demo of our caption generation model and visit our project page.